So, good afternoon, everyone, and welcome to this iMOVE webinar on Cooperative Intelligent Transport Systems, or CITS for short. I'm Ian Christensen, the Managing Director of iMOVE and your host for this webinar. I'm excited to have this opportunity to present to you the outcomes of two pivotally important projects that have just been completed by iMOVE and its partners. But before we get started, I have the usual housekeeping requests. So because there is a large audience, I'd ask you to keep your microphones on mute unless you're actually going to answer or ask a question at a later stage. And for questions, I'd prefer that you type your questions into the question and answer box, which you can access through the Q&A button, probably at the bottom of your screen, at the bottom of the Zoom window. So, Cooperative Intelligent Transport Systems. It's an important technology for us to understand and embrace. CITS has the potential to significantly reduce our national road toll, and simultaneously, we expect it will also increase the capacity and performance of the road network. iMOVE supports activities towards the development and adoption of CITS nationally, and today we're going to learn about two important steps that have been taken in that direction. The first is the Ipswich Connected Vehicle Pilot, or ICVP for some who like acronyms. So the Ipswich Connected Vehicle Pilot gives us insights into the safety benefits that come with these connected technologies. Today, we're going to be hearing from Dr. Merle Wood, who's the Principal Traffic Engineer at the Queensland Department of Transport and Main Roads, Jack Pinot, who's an engineer at the Queensland Department of Transport and Main Roads, Dr. Michael Pascal, Research Fellow at the Centre for Accident Research and Road Safety at the Queensland University of Technology, and Dr. Mohammed El-Henawi, Research Fellow at the Centre for Accident Research and Road Safety, also at the Queensland University of Technology. So for this section, Merle is going to be our leader. And so, Merle, I'm handing over to you.
All right. Thank you, Ian, for the introduction, and good afternoon, everyone. It's good to see so many of you have interest in the connective ITS topics, and it's absolutely our pleasure today to present our findings. My colleague from TMR and QT, we have done different parts of the evaluation, and we will discuss different part of our findings with you today. So everyone okay to see my screen, I believe? Yeah, okay, good. So before I start, I would like to acknowledge the contribution for so many parties. You can see at the bottom of the slides, there's a few logos here. So Maze and iMOVE, they have been tremendous support for us throughout this project. And of course, QT is our major partner here. They've been with us for the whole journey from the start of the study design, participant management, and also all the safety evaluation, user perception evaluation. They have been doing a really good job for us. And also Ipswich City Council, they have provided us a test site that we can do all our testing and installation, and also provide the wonderful participants for us, so we can do our pilot. Okay. Is it going? Yeah. So TMR have 5 strategic objectives. They are accessible, safe, responsive, efficient, and sustainable, leading to our greater vision of creating a single integrated transport network accessible to everyone. And so for the Ipswich Connected Vehicle Pilot, safety is the main theme for that, because we are trying to use this pilot to demonstrate the potential of CITS to reduce road crashes, so we can minimize our road toll or serious injuries to 0 in one day. And for this particular Ipswich Connected vehicle pilot, we have 4 objectives as well. So for the first one is we want to demonstrate technologies and then build the participants, the public awareness. So by recruiting the general public drivers in Ipswich area, so they can experience the CITS system in their own vehicle for 9 months. And then also we want to build our capability, our in-house capability and our partners. So one day when CITS become a normal thing for in every vehicle, everyone is ready for that. And lastly, of course, for this presentation is all about validating the safety benefits of the CITS system. Just some background about our pilot study. So you can see that the green shaded area here is the map of the coverage, where we have the cellular use case that will be issue warnings if there is if the participant entered the relevant area. And also why we choose Ipswich, because it's about 45 minutes away from the Brisbane. So a lot of residents here, they do travel. There are a couple of motorway options to go to Brisbane. So they will use a lot of motorway as well. And then we could test a few motorway use case. And also we have a few traffic light corridors in Ipswich that controlled by TMR. So we can implement all these use cases along, and also it's easier for us to maintain throughout the pilot study. So as you can see, there were 29 traffic lights that were instrumented with the CITS equipment. And from there, we have 2 traffic light use case and 4 cellular type. I'll explain that a little bit more later. So this is kind of like a high level architecture or the setup of this study. So in each participant's vehicle, they have the Coda install the vehicle station in their car. So we did all the installation of the 350 participants, and QT has been doing the recruitment, managing day-to-day correspondence between the participants and also the evaluation with us. And then for the roadside messages, they are all communicating between the vehicle and the roadside station with a short range communication. So it's a so captures the road station vendor, and then with the long range messages like communications, like the roadwork warnings and safety hazard, they were communicated by the cellular network here. And of course, we have a centralized station where we host all the data and storage in the AWS. And there are 6 safety use cases that we have developed in collaboration with our vendors. And on the left-hand side, we have 2 traffic signal based use case. The first one is these 2, like advanced red light warning and turning warning, is to provide participants warning in advance of any conflict within the, maybe like if we believe that they are traveling too fast, approaching a red light, or they are going to be having conflict with the pedestrian crossing during the green. And then the other 4 use cases are cellular based. And so the road hazard, so it's basically provide the driver enough heads up that the warnings of the road hazards or congestion on the motorways, roadworks in the area. And all these all come with the in-vehicle speed, which is the instantaneous, or where they're traveling, the speed limit of that current time. So some overall pilot statistic here. So after the 12-month pilot with 350 people, everyone were required to travel about 3 hours per week minimum in the pilot area. So we end up with all these numbers here. So we have over about 50,000 of red light warnings issued. The yellow column is meaning that they only have medium level, like a lower level of warnings. the red column, which means it's an escalator to a high level warning, which means that they really have to take action, not not to notify them there's a warning hazard. And the other, so with the traffic signal based use case, so the communication between the roadside unit and the vehicle station is 10 Hertz. So every 1/10 of a second, they have been communicating to make sure that the safety critical information is transmitted to each other. So latency has been a very important aspect for us to look at. And for the cellular type of warnings, we have much less amount, basically because the roadwork is not everywhere all the time, and so it's just when they occur or when the participant were driving close to them. And yeah, so it's you can see that there's a huge amount of data that we have to look at to provide some safety benefits. So we have two research questions here. So the first one is being with the CITS system, do they really improve the road safety, or by how much? The second question is the system acceptable to the drivers? So we look at this in two different ways. We call this side the safety driving response. Is the objective data that we've got. So it collects from all the roadside station, central station, and vehicle station. We look through all the data and messages for analysis. And also, we also undertook a series of user perception or surf questionnaires. So each participant would receive 4 questionnaires at different stage of their pilot study. And they get to rate their perception of their own driving, and as well as how the system performed. So with the participants, we have divided them up into different cohort. So with the 350 participants, 10% of them were assigned as control. Unfortunately, during that period, the 9-month period, they will not see any message. So they would just act as collecting data in the background for us. And so we can detect any seasonality effect and also any just like a baseline that we can see what driving behavior normal drivers should be. But at the end of when they finish the 9 months, we do offer them 2 weeks just to switch on the messages, so they can experience what message they get, the CITS, but we won't be analyzing their data during those 2 weeks period. Then the remaining 90% of participants, we divide them into halves, and then so we have one group that will receive the treatment first for 6 months. And then afterwards, they receive no warnings, so they act as a baseline participant themselves for 3 months. And then the other group of participants receive blank screen for 3 months, and then it will automatically switch on for 6 months. So it's like a switch, so they can balance the effect. So how do we prepare the data? Just like a high-level summary here. So we have been, because of the large amount of data that we have collected, we won't be able to analyze every single bit of information. So we trim our data to relevant safety scenario, which is like the event when they were near the use case. Usually we look at a minute before and after they encountered the use case. So the rest of the data, we can trim them off, and we don't need to store in our safety evaluation data lake. So it's easier for us to search through the relevant data for analysis. And also that can protect the participants' privacy. So we will be looking at only locations that we're interested in, and then we won't be able to establish where they live or where they work or where they normally shop. And also with all these scenarios, of course, we're not just looking at participants who receive warning, because for the control participant, we also look at the times that when they would have received the warnings if they travel like this way. So we can do a comparison before and after like that. All right, so I can pass it on to Jack to talk about some hypotheses and testing results.
Hello, everyone. So once we've done all this pre-processing and trimmed all the scenarios, how do we actually arrive at evaluating the safety of this system? And we've done this by selecting 3 hypotheses, and these hypotheses are selected because they're good indicators of the safety of the vehicle. We can actually convert them to a crash reduction and then scale them to 100% market penetration. So the most typical one you would have heard of before is low mean normalized speed. And so essentially what we do is we look at participant speed and we divide it by posted speed, i.e. the speed they're meant to be compliant with, and see if this changes when they receive warnings. Perhaps a little bit more abstract is our second one, low acceleration. And acceleration, as you can see in that figure on the right, it's essentially a summation of the absolute value of all these minute speed changes. So if we have someone that's slowly accelerating up behind a vehicle, we can see that all those blue bars are little bits of acceleration, and then they hard decelerate. So then we see that those red bars indicate deceleration. So essentially what we do is we convert all those accelerations and decelerations into one giant bar, so one value, and that is a participant acceleration. And that's good because every participant has acceleration, and evidence suggests that a person's acceleration is related to their crash likelihood. So a low acceleration means they're less likely to be involved in a crash, and vice versa. And our third hypothesis, which is a little bit easier to understand, is lower near crash. So we expected that people who are receiving these warnings are going to have a lower near crash than if they weren't, because of several things, including their increased awareness of scenarios. So we investigate all of these hypotheses. Next slide, please, Mel. Yep. So the way we've analyzed this is best explained by talking about the importance of these warnings. We need to analyze exactly what the impact of this warning is specifically. So there's no point looking at an entire trim scenario that Mel showed, because their acceleration, their mean normalized speed, and all these other hypotheses are going to get diluted along the entire drive. So what we wanted to do is we want to pinpoint exactly when they were getting these warnings and identify the change occurring because of that. So we created a bunch of different windows known as analysis windows to evaluate the impact of these warnings. So the most obvious one is along the warning. So as soon as they get this warning, how are they actually reacting to it? And we thought, okay, that's a good idea, but maybe they're not reacting straight away. So we analyzed from that point onwards until the end of the approach. And so when we look at that, we analyze the evolution of their behavior from the warning onwards. And we've also looked at that entire window of time. So it's a little bit more diluted, but we wanted to cover all grounds. And so it's also important to talk about here that some of our use cases have 2 distinct locations, an approach zone, as you can see, and an event zone. And so an approach zone in the context of a roadworks warning is once they've entered that area and they're getting a 60km/h speed limit posted, that is our approach zone. Once we enter that 40km/h zone where they're up close and personal to workers, that's an event zone. And it's important to distinguish between these 2 because studies have shown that people will react a lot different in an event zone to an approach zone. And so we see these 2 zones in this use case and also the turning warning for vulnerable road users. So when we look at all these different windows in these different zones, what do we see? Well, we saw that the people who are receiving the warnings in the approach zone have a lower mean normalized speed, and their acceleration is actually substantially lower when we look at that entire approach zone. Even in the event, we see that they have a lower speed along the warning, and throughout that entire event zone, from that 40km/h zone until they leave it, they have a substantially lower speed and acceleration. So when we scale this, it equates to approximately 50% reduction in work-related crashes at the roadworks specifically. Next slide, please, Mel. So the back of queue doesn't have an event zone, and it's relating to the congestion. So we warn people that there's congestion ahead, and so it's only as they approach this this congestion zone. And so when we look at the entire, so as soon as they enter that kind of approach, they enter a track where they count a congestion area, we see that the speed and acceleration is lower for people who are receiving these warnings. But when we actually look at that warning onwards, so we know they've received the warning and they should be changing their behavior, we see that the speed doesn't doesn't have a significant difference between HMI speed variation or their acceleration from the warning onwards is lower. So this indicates that they might be receiving the warning and coasting ever so slightly slower, and they're not actually going to abruptly brake once they encounter this congestion. Next slide, please, Mel. And probably one of the more difficult use cases to evaluate is the road hazard warning analysis. And so these scenarios are very rare. I think we ended up only being able to analyze about 600, 800 scenarios. And it's very difficult because the sample size is so small and there's a lot of variation in these road hazard warnings. This road hazard warning covers anything from faulty traffic lights to flooding to a vehicle on the side of the road. So it's very difficult to actually analyze these very rare events, and the behavior between the different events is very difficult to analyze as well. So when we tried to model this, we didn't see any significant difference. However, we're performing to that for the final report. So unfortunately, there's nothing too amazing to report for this use case, but we're hopeful moving forward. Next one, please, Mel. And so we see again another use case where we have an event zone, and this is a turning warning for vulnerable road users. So as someone's approaching a green light and a pedestrian stopping has been going, then they're going to receive a warning that indicates, oh, there's a pedestrian that's actually there's a vulnerable road user crossing this. And one of the big problems with it is because of COVID. And because COVID was in place, a lot of the main intersections were equipped with automatic pedestrian crossing. So someone didn't have to activate the pedestrian crossing for it to go. And the system is not able to recognize that this was an automated pedestrian crossing. So for 6 of the major intersections, we had to remove all the data when these pedestrian crossings were activated. And from memory, it was from the beginning of the fault until about the 18th of February, where we had to remove this data. Also, participants received some false positive warnings because they had a straight movement. This is specifically for turning movement. So when people are going straight and there's a pedestrian crossing activated that they're meant to turn through, they also received these warnings. So when we exclude all this data and we clean up a lot, we see that across this first warning, when they're approaching the pedestrian crossing, their mean normalized speed is lower across that warning window. And also when they're in the event zone, when they're past that actual approach zone, when they're past the stop bar and they're approaching that pedestrian crosswalk, we see that the treatment is significantly lower for acceleration and mean normalized speed. And one of the other things we want to analyze is a lot of these scenarios are joints. So they go through the approach zone and enter the event zone immediately after. And so we thought, why not analyze that entire evolution from the first warning all the way until they leave that scenario? And we see that the treatment speed and acceleration is substantially lower across that evolution of the warnings for the turning warning for vulnerable road user use case. So that wraps up my speaking for now. I'll hand it over to Mohammed, who's going to discuss the advanced red light warning and some of our initial insights into the near crash hypothesis.
Yeah, so advanced red light warning is one of the most complicated use cases we have in this trial. We started the analysis by using all scenarios with warning triggered, but we didn't find any significant, statistically significant differences between the on and off groups. So we decided to extend our analysis to focus only on the first vehicle in the queue. And also we studied the likelihood of the escalation from medium warning to high warning. And finally, we would like also to study the likelihood of running the red light. And by extending our analysis, we find that the likelihood of escalating from medium to high is actually reduced from 27% to 20% almost. And also, which means that when HMI is on, a driver would be more likely to comply with the medium warning, and hence this scenario didn't receive the red warning or the high level warning. Moreover, we find that there is a significant speed reduction between the HMI on and off within this subset of escalated scenarios. So next slide, please. And so actually one of our third hypothesis is that there is the likelihood of near crashes and crashes is lower between the HMI on group. And we followed we used three different approaches to detect near crashes in our data. So the first approach was only based on a threshold, a kinematic threshold, and these thresholds actually are adapted from overseas, from SHARP to a study. And using this threshold, we find only PAC-Q has a significant difference in near crashes. Moreover, we found that one of these thresholds is very noisy, which is a swerve. And actually, we are not the only group which reported this noisy threshold, but there are other groups which reported this swerve trigger is very noisy. And we, in the downstream analysis, we removed this swerve trigger from our analysis. The second methodology we used to detect near crashes is driving volatility. And driving volatility, it's simply a measure of deviation from normal driving. And third methodology, we used artificial intelligence, we used machine learning and an overseas data which has labeled crashes and near crashes to build a model. And then we use this model to detect near crashes in our foot data. And Jack will give us more details about the pre-processing and the testing of this machine learning algorithm. And so volatility measures, we used 6 different volatility measures, which are used to measure the deviation from normal driving. And we used also the historical crashes at the location, the intersection location, and identified motorway links to model the frequency of crashes as a function of volatility using the control participant. And once we did this model, we can actually estimate the expected crashes for the baseline and for the intervention and compare the expected number of crashes. And then we can estimate if we have a significant reduction in crashes because of HMI or not. So Jack?
Yep. I'm just conscious of time, so I'll very quickly go through this so I don't steal any of Mike's glory. So essentially what we do is we look at the 100-car data in the American data set. That's an example of a signal on the top left. Each of those, there's 828 crash scenarios. We take the very beginning of those scenarios. There's 30 seconds of normal driving and then a crash. We take the normal driving from that. We take the crash from that for every one of the 828 scenarios. We convert lateral acceleration, longitudinal acceleration, and yaw rate, those 3 base features, into 140 different features which look at different summary statistics: mean, minimum, maximum, median, standard deviation, variance, etc., over 1.5 to 3 seconds. And so when we have those 140 features, the model then attempts to differentiate between crash and baseline data because we fed this baseline data and this crash data to the model. And essentially, by following that flowchart from top left to bottom left, we end up converting that signal by creating some features into the probability of a crash occurring. So you can see that that longitudinal acceleration signal of baseline and crash ends up getting converted into that plot there, which shows baseline and crash in blue and red respectively. So if we want to talk about this a little bit further, I'm happy to take any questions, but I'll give it over to Mike so that he can actually get a chance to talk.
Thanks, Jack. So yeah, conscious of time, I'm going to speed through this as fast as I can. Basically, this is the timeline overview of what each participant saw in their 9 months. There was 4 questionnaires. The first questionnaire was completed before they had the equipment installed, and then they saw 3 remaining questionnaires spread out over the 9 months. And then during that time, they could also do interviews and focus groups afterwards when they were done participating. Okay, so this is just a brief look at our participants. The mean, well, we had 350 to start. The mean age was 46. Our oldest participant was 78 and the youngest was 20. split down the middle in terms of gender, and most of our participants had open licenses. We were restricted by the technology being installed in people's vehicles and being an extra display, so we weren't able to recruit new or learner drivers, but we did have 3 P2s in there. The final sample that we had at the end of questionnaire 4, or by questionnaire 4, was 326, and that was just the result of normal participants wanting to withdraw and some missing data. Okay. So these are the measures that we looked at. You know, acceptance is a pretty standard one. We used the unified model for driver acceptance. We looked at self-reported safety, differences in attention and perception. This is self-reported attention and perception, experiences related to the warnings and the HMI, experiences related to the use cases and general experiences in the pilot. And then in the most recent round of interviews and the focus groups, we also tried to get at some idea of what they thought future technology should do and what it should look like. Okay. So participants made their acceptance rate. Well, they made the ratings on most questions using sliding scales, which you can see here at the top. This is the overview of acceptance in of itself. So on the left side, they were making bad versus good, useful versus useless, and etc. And then on the right, they were agreeing or disagreeing to these statements. Just keep going. We'll get through this as fast as we can. Next slide, please. So for the acceptance measure, we wanted to investigate factors of time, so differences between questionnaires, conditions, differences in gender or due to gender, differences due to age, differences due to technology readiness, and differences due to risk. Our expectations were that participants who experienced the CITS would report greater acceptance. We ended up with some mixed responses. Generally, people were quite happy with the technology over the course of the entire 9 months. Ratings were just high, and that was maintained. We found effects of time, condition, age, and technology readiness. And we're still conducting some more fuller analysis, but we did find a small negative association in acceptance with after using the HMI. So there was a small decrease after participants first experienced the HMI. Yep. So the same regressions we applied to the other measures as well. Just to run through the analyses quickly, we expected that participants would report more safety while they're driving, positive effects on attention, perception, and the display as a distraction, greater effectiveness of the warnings in terms of timing, the content, and the imagery, and greater usefulness of the use in terms of each of the use cases. And that's compared to the control group. Initial analyses were again mixed, but responses were generally positive. And Glenn, to answer your question, they did report that the device would be effective in capturing their attention and not be a distraction, whereas the control group sort of didn't really know what to do. So the people who saw the technology reported higher levels of attention and lower levels of the distraction compared to the control group. I know you're going to jump in 1 second, so over to you, Merle. And Glenn, to answer your question, this is what the HMI looks like here as well.
Okay. Yeah. Sorry, I've been mute. So just a quick summary here. So yeah, with all the speed and acceleration analysis that we have done so far, we see that some of the use cases have promising results showing like significantly lower speed and acceleration with the treatment participants. But yeah, there's a few tricky ones that we still need to spend a bit more time to refine our model and analysis. So hopefully in future we can come back to present the actual results to you, and with all the near crashes stuff as well, once we're all fine-tuned. And it's also echo what Mike said. Usually generally the participants have rate the system highly, although we see a slight decline of their ratings over time, but we generally see they are still quite happy with their experience. Is that right? Yeah, so our presentation's here done. So I'll just hand over to Mao. Is that right?
So I will step in and say, first of all, thank you, Merle and Jack and Mohammed and Mike. It was it was a huge project. You've collected a lot of information, and I think so much information that you're still working through it. But I think it's also true that some of the participants liked it so much that they actually wanted to keep it going. They wanted to keep the equipment in their vehicle. So that's an exciting observation. Unfortunately, we're now running a little bit behind, so I'm going to defer the questions and answers to the end of today's webinar. But I would encourage my friends at TMR and CARS-Q to have a look at the questions in the question box so that we can answer them clearly at the end. But for now, we need to go to the second project that we're going to report on today. And this one is another significant step forward in the use of CITS to create safer roads. So Cooperative Perception is the name that's given, the umbrella name that's given to the work that Coda Wireless and Sydney University have done here. And this is technology and techniques to draw conclusions from multiple inputs so that we can help vehicles and drivers see hazards that they can't see physically. So for instance, if there's a cyclist hidden behind a bus or a car hidden around a corner, hidden by a building, then Cooperative Perception is a technology that enables those hazards to be revealed to the individual drivers. So to tell us more about this, we're now going to be joined by Professor Eduardo Nebo from the Australian Centre for Field Robotics at the University of Sydney, Professor Paul Alexander, who's the Chief Technical Officer at Coda Wireless, and Dr. Mao Shan, Research Fellow at the Australian Centre for Field Robotics at the University of Sydney. I'm going to leave it to you guys to organise yourself, but I don't know, Eduardo, are you going to take this out?
Yes, thank you very much, Ian, for the introduction, and good afternoon to everyone. This is a project that is a joint collaboration between the Australian Centre for Field Robotics and Coda Wireless as part of the iMOVE CRC effort. ACFR is one of the largest field robotics labs in the world. And within ACFR, we have a number of groups. I mean, and one of the groups is the Intelligent Transport System groups that has been working in research and development for autonomous urban vehicles for the last 10 years. And during this time, we have developed and implemented a number of autonomous vehicles with communication capabilities. As part of our work, we do fundamental research on developing in different areas in perception and scene understanding. Autonomous vehicles platform, we have done a lot of work with different platforms and working with some local companies. We do work in path planning and safe trajectories. And the group, I mean, that has a history of being the leaders of in localization, been generating all the fundamental concept of SLAM. And in terms of this project, we do a lot of work in robust localization and map maintenance. And in other areas, we do work in safety assurance and driver pedestrian intentions. It's very interesting to say that during the years, I mean, we have also developed a very flexible autonomous vehicles technology stack. And this is very important because this technology become very flexible, and it allows us to incorporate capabilities such as cooperative perception. This allows us to develop a new concept in the area and perform very comprehensive demonstration, including multiple connected autonomous vehicles, as you will see today. We are also, I mean, working with transport in order to facilitate the introduction of autonomous technology in Australia, and we are going to be extending all these concepts to the Future Mobility Center in Kudal and Orange. Next slide, Mao, please. Something just to mention, I mean, that As I mentioned before, I mean that during the last 10 years, we developed a number of platforms and we developed all this technology. And for this, it was essential the contribution from the different sector, industry and government. Of course, we have the great support of the University of Sydney, but at the same time, I mean that we have a number of projects with iMOVE CRC involving transport using well, of course, Coda wireless, as you will see today, and insurance companies like AIG. And also we have existing, I mean, that the collaboration with external institutions, I mean, like University of Michigan for motor companies and to extend Renault, and with local companies like Apply Ruby and Blank Robots and Baraja and the existing collaboration of IBO. Okay, so with this introduction, I'll leave Paul, I mean, that to enhance the contribution of the center and the Coda wireless.
Right, thanks, Ed. Thanks, Ian. So yes, hope you can hear me okay. So really, I'll just give a few words about why Coda is interested in the project and a little bit of background, which I might skip through pretty fast, mouse. It'd be hot on that mouse. So you'd be aware that perhaps Coda is involved in V2x Communications Globally. What is V2x Communications? Well, it's about connecting the vehicles to infrastructure, people and other cars for the purposes of safety and traffic management principally. So one of the objectives was focusing on safety. There's a promise of about a 50% reduction in crashes, and that's been reported for a number of years. V2x is starting to roll out now. The next slide, please, Mount. So the way it's rolling out is there's essentially 2 or 3 message sets, but the hardware and software stacks underneath it are reusable. It's just the top level bits of software that need to be changed. So there's a probably 50 different kinds of messages globally that can be supported. I would say the standards groups, this is all standardized, of course. The standards groups have pretty much contemplated every use case you could think about, going from basic awareness, which is where are all the other cars around me, irrespective of whether or not I can see them, through to event-driven messages such as the denims in Europe, and then some signal phase and timing and vehicle messages. Another message type is collective perception messages. So really, quote unquote, we're just talking about another message type. There's much more to it than that, but I suppose the point here is that there's been standardized a way for vehicles to share what they know or what they have seen, and importantly, roadside units to share what they know and have seen with other vehicles. There's a parallel universe in the US here in terms of message sets. I won't dwell on C-V2X and cellular and DSRC, that's a whole other topic. Next slide, thanks, Al. So what is cooperative perception? So it's, I think Ian and Ed touched on it gently. It's really about having the driver or the autonomous system in a vehicle be aware of things that it can't otherwise perceive, either through the human or the sensors that are on board an autonomous vehicle. If you think about an autonomous vehicle, it's actually pretty normally equipped with line of sight sensors, right? LiDARs and radars. So what we're trying to do here is bring the line of sight sensing capability of an RSU or another vehicle to a third vehicle. So the bottom vehicle there can now benefit from what an RSU can see or what another vehicle can see. I suppose V2x was conceived at day one around this principle. So connecting the vehicles directly is a non-line of sight capability. So you're aware, your vehicles are aware of each other, even though they might be around corners. So this is all kind of conventional V2x stuff, but now supercharged. We're really trying to bring this perception world really to the maximum. And of course, it's not easy to do. There's a lot of challenges in doing this. So from Coda's point of view, what we wanted to do with this project, and I'm very pleased with how it's panned out. So thanks to iMOVE for helping with the funding and the ACFR for the great work. We've really been able to show and de-risk some of the technical challenges in doing this. And I'll just briefly mention a couple of those. One is timing. Another one is the pose of the vehicle. So it's no good sharing something from your vehicle if you can't calibrate and understand what your vehicle is actually doing. Then it's all got to be compressed over the air in a compressed message set. So a number of challenges. Coda is very interested in that, and we have deployed this to our own autonomous vehicle platform. So outcomes that have been generated principally by the ACFR have found their way into our own vehicles. Next slide, please, Mal. And we actually have a a YouTube video that we prepared, which there's a link there. If you can, we can share that out afterwards directly. That shows why we think CPM is very important. And yeah, I would invite you to have a look at that video after the fact. I don't have time to go through it here. Next slide and final slide from me. Just the project timeline. So what we started with was getting an intelligent roadside unit going. So what is that? It's a piece of roadside equipment that can see things based on camera-based classifiers or LiDAR-based classifiers, encapsulate that into standardized messages according to the standards I mentioned, and then send them out to the cars, step one. So now that car there on the right is aware of what the roadside unit can see. In other words, it can now see around corners, etc. Then we bring the second vehicle into play. So fast forward now, yep. So having multiple vehicles there where vehicles are in receipt of perception information, both from infrastructure and from other vehicles. And it's that other vehicles one, which is really the gold standard because of the aforementioned issues. So that was a bit of a machine gun presentation, but I'll hand over to Mao now to present the details. Thanks, Mao.
Okay, thanks, Ed, and thanks, Paul, for the introduction of the project. So it's my great pleasure representing the joint research team from ACFR and from Coda Wireless to present, a summary of what we have achieved during this project over the last 3 years. So this will be the structure of the remainder of the talk. So as mentioned earlier, like Paul mentioned, intelligent infrastructure is a really significant component in cooperative perception. But let's look at, what makes the intelligent infrastructure required in CP different from those in the existing projects. So here I list a few examples of Australian ITS projects that involve intelligent infrastructure. So there are smart motorways in New South Wales, and in Queensland, Western Connect and Transmax. And so both of them have an incident management system in place, where cameras are deployed along the motorway to monitor traffic and detect car incidents and have the information forwarded back to the control center. There are also 2 V2x trials. So one is a V2x free priority trial in New South Wales, where free trucks are given priority when they are passing traffic lights so as to reduce traffic congestion. So the other one, Ipswich connected vehicle pilot, is exactly the project the previous session was talking about. So we've already learned a lot of information from there. So it was a wonderful project. So both of the V2x trials focus on the use of existing standard V2x messages. However, none of the existing messages is meant for CP use case. So there are 2 features required in the intelligent infrastructure for CP. So first thing first, so it's required to have sensing capability to detect and check common road users in real time, like cars, like vulnerable road users, including pedestrians and riders. So in the meantime, it's also required to share the perception data out in the form of a standard V2x message, for example, the ADC CPM message, to ensure interoperability across different manufacturers and devices. So ADC CPM, it's a new message type, and it's designed just for CP purpose. And this is a message that we use in this project. So look into the future, given an intelligent infrastructure that has a sensing capability and a V2x communication capability, we actually can do a lot more things. So CPM is good, but it's still limited to sharing basic pose and kinematic information on objects, including position, velocity, or heading. So over time, infrastructure is becoming more intelligent thanks to the advancement of perception algorithm. So here we have 3 examples of perception techniques developed in our research team. So one is, we have the deeper learning network that can, extract the skeleton information of pedestrians, like the limbs, like body, head, gestures, hand. And also we have a network that can, get the semantic labels of the environment, including road, like trees or buildings. We have network that can predict the future trajectory of pedestrians. We have network that can infer like driver intention at a roundabout. So sharing these learned information on top of what CPM contains, can open up many possibilities of future ITS, CITS applications, and essentially making our roads smarter and safer. So in this project, we in total built 2 intelligent roadside unit prototypes. So the first one is the turbo prototype A. It's equipped with a 16-beam LiDAR and multiple cameras. There's a workstation that performs LiDAR camera sensor fusion for multiple road user detection and tracking in real time. And the roadside unit also encodes the perceived objects information into ADC CPMs and broadcasts the message out through this Coda wireless MK5 RSU. So last year, we built a lightweight and more portable version, Prototype B, which only has an RGBD camera as a main sensor and a single board computer for data processing. So it has a small form factor and it's battery powered. So as you can see, most of the components can fit into a watertight case. So although the detection range of this RGBD sensor is not as great as a LiDAR in the first prototype, but function-wise, these two prototypes are pretty much the same. So as for the vehicle platform, we use these two electric vehicles that have been retrofitted with a suite of perception sensors, including a multi-beam LiDAR and 6 cameras that can cover 360 degrees around the vehicle. So the vehicle can use its onboard perception sensors to track the surrounding objects and can achieve full autonomy in a campus environment. So what you are looking at right now in this video is the autonomous transit on demand using the vehicle. So now with the add-on of the Coda wireless MK5 OBU, this autonomous vehicle platform is turned into a CAV, the connected and automated vehicle. So I would like to briefly talk about 2 important techniques used in CP within the CAV. So what you're looking at right now is a common perception pipeline that can process sensory data from its local sensors. But now through the V2x communication, the vehicle can also receive remote perception information from other ITS stations like other connected vehicles or intelligent infrastructure. But as Paul mentioned earlier, this information contained in the CPMs is registered in the sender's coordinate system. So it has to be transformed into the receiver CAV's local coordinate system before it can be fused into its current perception pipeline. So this coordinate transformation is also referred as time and position alignment in the literature. So we stress that the coordinate transformation process also needs to consider, the perception uncertainty you are looking at right now, and the sender's localization uncertainty, and finally the receiver's localization uncertainty. So in the end, the final uncertainty of the information after transformation is a combined result of the 3 uncertainties. So the other important thing to note is that you won't know how much the perception data in the received CPMs is correlated with any prior information. So this brings the risk of double counting of information, so which leads to over-optimistic estimation results. So to solve this, we propose to use covariance intersection in the data fusion, which can safely fuse the remote perception information with unknown correlations. So now I want to present a series of demonstrations to show from 5 different aspects how CP can make our roads safer. So first of all, it's demonstrated that CP can help vehicles see around corners. So this is a demo conducted in a real urban traffic environment. So the connected vehicle, was driven from this side road here to the main road before it made a right turn to this alleyway. So the visibility for the turning is very poor due to the occlusion caused by this building. So the roadside unit was deployed here to monitor the main road and the alleyway. So as you can see, before the vehicle turned into the main road from the side road, it's already receiving the CPM from the roadside unit deployed here and knowing what's going on the main road. So when the vehicle now, when it's approaching this this alleyway, so I will pause here. So actually right now, there was a hidden pedestrian behind this building, but it couldn't be seen by the driver and the vehicle sensors due to occlusion. However, thanks to the roadside unit and the CP, the vehicle received this critical information, like you're seeing here, this information like seconds before the hidden pedestrian can be visually picked up from the vehicle's perspective. So this shows that the vehicle can see around the corners using CP so that it can consider this safety crucial information in its decision-making process. So the second one is demonstrated that CP helps automated vehicles avoid collision with road users. So this demo was conducted in a simulator in color. So one of the benefits of using a simulator is that it's a safe playground for us where we can have our algorithm fully tested before we test it in the real world experiments. So in this video, in this demo, so what you are watching right now is this CAV, this vehicle without any onboard perception sensors can safely interact with stray walkers only using the information from the roadside unit. The roadside unit is deployed somewhere down the road. It's visualized as like a car next to the road. So to avoid this stray walker, so the vehicle planned a new path to avoid it, it switched to the other lane, and then after that it switched back to the original lane after the avoiding maneuver. So now this is another scenario where two jaywalkers they are blocking the entire road. So the CAV had to decelerate to stop, wait there until there is enough space for it to navigate around them. So in both scenarios, the CAV made all these decisions by itself using only the information from the roadside unit. So next one, so it's demonstrated that CP helps automated vehicles know what's to come. So this was a demo conducted in a lab environment. So the CAV was driving by itself towards a designated pedestrian crossing, and the roadside unit was deployed, here to monitor the crossing. So there was a pedestrian in the demo. It was actually myself running towards the crossing. And the CAV learned from the roadside unit that there's someone approaching the crossing, so it stopped in front of the crossing for me to give way until the crossing was clear. So these are the same thing, but from the roadside unit point of view, and this is the same thing from the vehicle's point of view. So based on the current position and the kinematics of the pedestrian received from roadside unit, the vehicle predicted the pedestrian's future position and reacted accordingly. So maybe it's not so clear in the videos, but here I have a graph to help you guys. So the dashed line marked the exact moment when the pedestrian physically stepped onto the crossing, but the CAV started deceleration almost 2 seconds before that happened. So this shows that CP can help the CAV gain extra reaction time for upcoming safety threat. So in a traffic context, I think 2 seconds can make a huge difference in terms of safety. So next one, so it's demonstrated that CP helps automated vehicles see road users more clearly. So this is similar video, similar demo as the previous one, but with a more complicated setup. So another connected vehicle was here to monitor the same crossing area. So this CAV, again, this time is receiving CP information from both the roadside unit and from the connected vehicle through V2I and a V2B communication. And it performs data fusion to generate more accurate and reliable estimate of the pedestrian. So as you can see from those two pictures, before fusion, so there were two pillars representing two pieces of perception information received from these two external sources. And then they are fused together to produce a single estimate with a smaller uncertainty.
Mao, just could you excuse me for a second to say that we're going to continue this webinar for another 15 minutes. I know that some people will have to leave us at 2 o'clock or on the hour. So for you, we will make the webinar recording available on the iMOVE website. So you'll be able to catch up, but we will continue. For those who can stay, we're going to continue for another 15 minutes.
Thanks, Ian. Thanks, Ian. So this is the last demo I'm presenting. So this is a demo that CP helps automated vehicles safely handle intersections. So I think turning right at an unsignalized intersection is not an easy task even for human drivers. So here we're actually looking at a demo conducted at within the Sydney Uni campus. So the CAV needed to make a right turn at this T-junction, and it has to give way to any incoming traffic on the opposite lane according to the traffic rule, and also make sure there's no other road users in this T-junction area before turning. So we have the roadside unit here. So this is a prototype B deployed here, and another connected vehicle parked here to monitor the whole T-junction area jointly. So again, the CAV didn't use any onboard perception sensors, and it performed the fusion of the perception data from the two sources, from the roadside unit, from the connected vehicle. And let's see what happened in this demo. So now the CAV is approaching and stopped in front of the T-junction, waiting for this white RAV4 to turn left at this T-junction. And not long after, actually, there was a public pedestrian who entered the T-junction area. So the CAV had to wait there for an extended period of time. Finally, when the CP system advised that the T-junction was fully clear of road users, the CAV started turning right safely. So I think to this point, we are in a better position to answer those three questions. For example, how can CP make our road safer? We have demonstrated these 5 safety-related aspects of how CP can help CAVs and essentially make our road safer. So how can CP shape the development of AV? I think one of the challenges for an autonomous vehicle to hit Australian roads is high cost, and its onboard perception sensors account for a significant proportion of the cost. But with CP now, the perception is achieved not by an individual vehicle, but collectively by vehicle fleet and the infrastructure in the local region. So this can substantially help an autonomous vehicle reduce the reliance on the local perception sensors, and thus lower the per vehicle cost. So lastly, for this question, we already shown in the demonstration that using the cross-platform data fusion, we can combine the perception information from multiple sources and produce more accurate and reliable estimate to the CAV. So now let's look at the big picture. This is the final slide. So over the last 3 years, so we've developed a roadside unit and the CAV platforms and a set of algorithms that can enable CP. Also, we have developed and tested an autonomous driving stack, which has proven to be working very well in the campus environment. So we've also accumulated expertise and experience in different research areas. So more importantly, we always focus on testing algorithms using real platforms in real environments. So for the future work, we would like to push our current CP work to the next level. So we are looking at opportunities of deployment of our CP technology and on-road trials in Coda, followed by Orange, New South Wales. Also, as I mentioned earlier, we can explore augmenting the CPM with additional information, for example, future path, intention, learned features, etc., which can trigger more future CITS applications. So we call it a CPM+. So lastly, we've done some preliminary work in cooperative driving. So what you can see from this video actually is a cooperative lane crossing using V2x communication. So I will leave this page running. So yeah, that's the end of this talk. Thank you.
Thank you, Mao, and thank you also to Eduardo and Paul for your contributions to this really quite profound step forward in terms of capability for safely navigating intersections and the roadway around hazards. So we now get to ask some questions and get some answers. To the audience, I would invite you to focus first on questions for around cooperative perception for Eduardo and Paul and Mao, and then we'll go to some of the other questions that have already been raised around the Ipswich connected vehicle trial. But I'm going to start first with a kind of a question following on from Mao's last comments on the things to do next, the further developments or that should be made. To Paul Alexander, from Coda Wireless's point of view, or from the point of view of actually building a device and deploying the technology across the community, what are the next steps that Coda Wireless would like to see happen to make this technology real or accessible to the community at large?
It's a good question, Ian. So really from our point of view, I think it's standards first. So we have to get the standards sorted out. They are not yet done. And actually, we didn't mention that some outputs from this work actually went into ETSI. So we actually did provide some feedback. So yeah, we have to have the standards done. But Europe seems to be ahead of the US so far on this, let alone the additional features that Mal was talking about. So CPM plus, as he called it. Yeah, there's several things that have to happen. I would add in there a scalability test. There's already been quite a lot of thinking in the standards groups about making sure that all of this data can actually fit on the air. So we have to be very aggressive in the compression of what we can share. Imagine if every car was sharing its raw LiDAR data. This is not possible, right? Even every vehicle sharing all of the 100 things that it might be classifying using its LiDAR camera radar system might not be possible. So there is some work to do on the standards. I think that's how I'd summarize that.
Thanks, Paul. Could I ask a sort of a small follow-up question? So I think or maybe to Mao, in the work that you did, the cooperative perception was established in the roadside unit effectively. Is that the case? And if that was it, or was it, is the cooperative perception established jointly in the roadside unit and the vehicle? Because in a sense, the computational load will fall to wherever the combined picture is created, I think.
Yeah,
and so
I think,
where does that best belong in the future?
So maybe I could attempt to answer that a little bit. So roadside units are very interesting because they get to see and hear from a plethora of vehicles more easily perhaps than a vehicle by itself might. It's not always true. So the RSU is in a good position to rebroadcast in a way, right? But V2x is a non-line of sight capable technology anyway. So if a vehicle around a corner transmits some perception information, yes, the RSU can pick it up, but your vehicle can also probably pick it up directly. So there are some interesting scalability questions there. I think to answer your first question, the sensor fusion is done at the receiving end in the vehicle. So as one of the vehicles that Mal talked about is receiving information from the roadside unit, and it's receiving information from another connected vehicle, and it's fusing all that together into one coherent picture.
Yes, exactly. So for the last demo, you saw, the T-junction part. They intentionally set it up such that the roadside unit actually was taking care of all the fusion. So it's doing the heavy lifting inside. So so that the CAV actually, it's just receive the positive result directly. It doesn't do any onboard computation there. So just this way is only to explore the idea of letting the roadside unit taking care of all the the heavy lifting part.
Thanks, Paul, and to Mal for that answer. But that opens the way to another question that came up regarding the first section. So I'm going to ask Merle the question that Glenn Gears asked about the number and the rate and the acceptance by the drivers of all the alerts and warnings that are going to happen, because you already have in your field trial a range of hazard situations that were generating alerts. And if we think about cooperative perception, that's going to generate a further set of alerts or warnings that will be conveyed to the driver. And ultimately, is there is there a risk that the driver will become confused or overwhelmed by the amount of communication coming to the driver from the system?
It probably is hard for me to answer this question because I think it's really by the design. I think in our design, we have kind of like a minimalistic approach. Is like we just want the warnings to be appearing in a flash of seconds. I think it's not staying on and keep beeping them. So they only have audio warnings when it's high level warnings. That's one thing. So yeah, but I think with the cognitive ones, it's probably they have to design in a way that to minimize the distraction. Right, Mike? Do you have any?
I can jump in here as well. So we did spend a lot of time considering alarm system research and nuisance alarms versus false alarms, and trying to find a balance, given that we were designing a one-size-fits-all approach for all drivers. And in that process, we did have experts from a few different areas come in to test the display under different conditions, trying to look for different ways that it would be distracting or startling. We went through various changes to brightness. We used different sounds, different audio volumes. We tried to use audio that was relevant to the ambient noise. So it was dynamic in a way that was trying to, be alerting, but also not too loud at times. So there was a lot of consideration that we did trying to create these systems in the best way possible. But at the end of the day, participants, it was a one-size-fits-all approach. So some people weren't happy with it. They thought it was coming too late. Some people thought it was less helpful or didn't increase their awareness as much. We did find that older adults were really happy with the system. They were quite willing to accept whatever they would get out of the system, even if it wasn't as helpful. Whereas I think younger adults were expecting it to be more accurate every single time. So we had a wide range of people who had a wide range of expectations, but we did try to design the system as best as we could to limit distraction and increase attention in an effective way. And that also included eliminating a bunch of system messages so that anytime the system came on, it was relevant to them from a safety perspective rather than a connection. They didn't need to know that it was not connected anymore. They didn't need to know the status of the connection. They just needed to know if and when they needed to slow down because something was happening in front of them. So lots of consideration in there. Obviously, you could talk endless about what we did, but that's sort of the brass tacks of it.
Thanks, Michael. I was sure that you had put quite a lot of work into thinking about the interface between the alerts and the driver. So I'm pleased that you're able to share some of that with us. One of the very first question that we got from Ken Fitzsimmons was, did you actually have any crashes in Ipswich?
So involving the participant, we had some, but it wasn't because of the warning. So it was just outside the scenarios, or when they parked their car, unfortunately, they just got run into. We have asked participants to report to us as soon as they had any crash, or if they need to take it to the repairer. So I think as far as we know, we only got a dozen of crashes that have been reported to us. Is that right?
Yeah, and it was typically after the fact. They were focused on doing whatever they needed to do. The first reaction wasn't to call the ICVP and say, "Hey, I got in an accident." So we asked them to come and give us as much information as they could, but it was typically delayed by weeks or months. And by that time, some of the context was missing, and it was a blur in most cases anyway. So it was hard to. We really wanted to get that information. That's obviously very useful, but it's difficult to get participants to pay attention that much, and also to provide that information in a timely fashion.
Yeah, sure. So Merle, just before we finally finish up, what would you like to do next at Ipswich?
Well, we have other use cases. I think it's been also we want to test, and also we want with the new version of the pilot study, we're looking into having portable units, so the participant can install the unit themselves rather than they have to come in. So it will be more mobile, and also we want to roll out to a wider locations.
Yeah. Fantastic. So we now have finally run out of the extra time. So it just remains for me to thank everybody for participating, thank the panelists for their huge input, the audience for being such good listeners and for asking so many interesting questions. We will be making the webinar recording available on the website, and we'd be very pleased to talk with any of you who've got questions, thoughts, suggestions, ideas for what to do next. We think this is a really important part of road safety research and vehicle research in Australia and into the future. So we're keen to support you in whatever endeavour you're trying to achieve. So with that, I'll say thank you very much. Thanks for a great webinar, and we'll see you at the next one. Thanks.
Thanks, Ian.
Thank you.
Thanks, everybody.